Demonstrating registration process. A user has to register for the first time when he downloads the app. Basic information like first name, last name, username, email ID, phone number is requested. Along with these details, gender preference and preferred mode of travel is also noted, so that we can recommend future fellow travelers based on users' personal preference. Demonstrating login. After successful registration, user can log into the app. After logging in, a secured token is generated and stored in in-memory storage of Android app. So that, next time user don't have to remember the password and he can access the app straight away. Demonstrating daily commute use case. One of the use case which has been addressed by this Yatra app is to allow users to find compatible fellow travelers to share a journey with. In this mode, a user can enter his travel plan well in advance and he can find the fellow travelers who are looking for co-travelers to share the journey with. Consider a case of two travelers on Yatra platform named Kevin and Peter. Kevin uses car for traveling to office located in Docklands in Dublin. He enters his daily travel plan in app from Houston Station to Docklands. Let's say he updates his co-traveler gender preference and preferences like mode of transport, journey frequency, start date and time. Consider a case of Peter. Peter also works in one of the offices within Docklands in Dublin. If he enters his travel plan with source and destination located within 500 meters and start time of the journey within 15 minutes buffer. He will then be paired up with Kevin and they can further plan their journey and share ride with each other on daily basis. As you can see, Peter is recommended with Kevin and few other fellow travelers who are sharing the same route.
Ad hoc journey planning can be done without internet connection. For the offline usage of maps, user needs to download the maps to the device storage. Here user downloads the map of Sandyford region and saves it to the device storage by providing a name. This map then can be used without network connection. This is a demonstration of Kathy, Karen, and Monica's ad hoc trip plan without the need for the internet. All of them have a preference for the same gender. They all select a destination within proximity and start a search for fellow travelers. The app searches for peer travelers for 1 minute and populates a list with the details. Also, The application selects a group leader based on the least request initiation time. Other group members are navigated to the location of the group leader. Group leader gets status updates in the list from other members. Here Monica and Kathy's status changes from seeking fellow traveler to first traveling to start point and later to reached start point. Once all the group members reach the starting point, the group leader can start the journey to the final destinations. To rate the fellow travelers, every member of the group is navigated to the user rating screen after reaching the destination. Once the rating is provided by the user, the application saves the user ratings in the local app database and reloads the home screen. New user ratings saved in the local app database are later synchronized with the backend API when the internet connectivity is restored. An updated user rating can be seen in the settings screen. Consider Kathy, Monica, and Charles planning an ad hoc trip. Kathy and Monica have the gender preference set as female, while Charles is looking for male co-travelers. All three travelers have the destination in proximity. Kathy can see Monica in the list of fellow travelers while Monica gets the details of Kathy. However, Charles's name gets filtered by gender preference setting and it is not shown to Monica or Kathy. Also, Charles has not shown any peer traveler on the list. Consider user J who has no network connectivity, but wants to schedule an ad hoc trip. The user enters the destination and starts to search for peers. As no peer is found, he starts the navigation to the final destination alone. Once the user reaches the destination, the navigation stops and application returns to the home screen.
Demonstrating unit tests. Unit tests are the fundamental tests in app testing strategy. By creating and running unit tests against code, we can easily verify that the logic of individual units is correct. Running unit tests after every build helps you to quickly catch and fix software regressions introduced by code changes to your app. Demonstrating instrumented tests. Instrumented unit tests are tests that run on physical devices and emulators, and they can take advantage of the Android framework APIs and supporting APIs, such as Android X Test. Instrumented tests provide more fidelity than local unit tests, and they ensure that basic workflows are intact as developers are merging changes. This test suite simulates workflows like login, registration, peer-to-peer discovery. It evaluates whether form validation is working correctly and fails otherwise. So it helps app developers to ensure that they are not breaking existing features due to new additions. Demonstrating continuous integration and continuous deployment workflow. Continuous integration is a software development strategy that increases the speed of development while ensuring the quality of the code that teams deploy. Developers continually commit code in small increments, at least daily, or even several times a day, which is then automatically built and tested before it is merged with the shared repository. Let's quickly see how the CI/CD pipeline is working for Yatra services. Whenever developer or content publisher creates a new branch of code in GitHub, updates the any source file, and then commits the changes. When the developer has completed all the changes on the particular branch, they then create a pull request on GitHub. For demonstration, we are directly committing the changes to master branch to trigger the build pipeline. GitHub is integrated with Circle CI. Circle CI fires up the Docker container as soon as it gets triggered via a webhook from GitHub. It runs build processes and then runs the automated test scripts. If Circle CI encounters any errors or test failures with build status red, the developer is notified via email. Otherwise, the user is notified that the build was successful green and that the code has been pushed to the respective deployment server. This allows the developer to preview the changes made to the services in real time. After successful build, the coverage report is pushed to the repository and it verifies if the recent changes is decrementing the code coverage or introducing any complications like cyclic dependencies. After successful build, Circle CI triggers Heroku deployment pipeline. In this step, the deployment artifact is pushed to Heroku. The Heroku platform provides free development server where the service is deployed with the new version. The real-time deployment can be viewed on Heroku dashboard or Heroku CLI tool. This entire process helps ship better quality of code and make developers' job a lot easier. The cloud services used by our application are highly scalable, available, and secured. Our system uses horizontal scaling mechanism to eliminate single point of failure and support growing amount of work, without loss of performance. We deployed 4 Dockerized instances of our services and distributed traffic among them with the help of a load balancer. With this approach, our cloud services can scale infinitely, and serve the increased demand by reducing the load on individual instances. An Nginx load balancer is used to distribute the incoming traffic across the pool of horizontally scaled instances. It uses round-robin algorithm and cycles through a given list of servers and sends each new request to the next server. Since most of our services would be read-heavy, there would be lots of redirection requests as compared to write requests on the database. For example, a new daily commute would be created only once, but list of fellow travelers would be retrieved quite often. Thus, to improve reliability, fault tolerance, or accessibility of our cloud services, we introduced master-slave replication to manage our Postgres databases. We also implemented centralized log management system to collect logs from all running instances. We used Elk Stack, which includes Logstash as a log aggregator to persist logs at a single collector host and eliminates the need to log rotate. This dashboard lists all running instances in the backend infrastructure of Yatra services. There are 4 application servers, handled by a load balancer. There is a master database instance along with its replica. The Logstash instance collects logs from hosts and hands over to the Elasticsearch instance to index and store the logs. These logs are visualized using a Kibana instance. To profile our system under varied loads and understand its behavior, we used Locust, a distributed, user load testing tool. We performed a Locust test which logins 1,000 users, spawning 100 users per second, into our Yatra application. Each user then fetches the journey details from the daily commute service. As we can see, our infrastructure successfully handled bursty as well as slow and steadily changing traffic. Our infrastructure is serving 90 requests per second on an average, with only 2% of failure. The logs from all running instances are visualized through a Kibana dashboard. We can see that the Locust requests are being served by all 4 instances of our application. Our infrastructure is highly available. The load balancer keeps track of the status of all instances while distributing requests. Thus, in the case, if we crash application instance with IP address 172.22.0.9, we still have 3 other servers capable of handling incoming requests. We can spot this slight glitch in the locust report, as at that moment, the load balancer updated its status log to eliminate the crashed instance and system failure. We can observe that the application instance with IP address 172.22.0.9 is removed from the pool. And now there are only 3 instances serving the incoming traffic without suffering any downtime. To make our databases fail-safe and avoid complete loss of information, we implemented master-slave replication in the hot standby mode using Bitnami Postgres Docker image. Thus, even if the master database crashes, the replica instance can still serve the read traffic, thereby eliminating the single point of failure, and enabling partial availability. It is evident that the locust requests are still being served by the infrastructure, as the replica database is serving the read traffic. To protect against DDoS attacks, we implemented rate limiting mechanism in load balancer. We limit incoming requests of each unique IP addresses to the request rate of 5 requests per second, a value typical for real users. When the incoming requests from a specific IP address exceeds the request rate, Nginx load balancer does not forward these requests to application instances, and simply returns status code 503, service temporarily unavailable error, to the client. To test security aspect of our services, we reproduced DDoS attack on the login API of Yatra services using a Python script. We can observe that the load balancer restricts the requests that exceeds the request rate limit. This fortifies our resources against a DDoS attack, thereby making our architecture as resilient as possible. Thank you.